equilibrium, we're going to use that information to help explain and describe how that affects our acid-base chemistry, specifically when we perform acid-base chemistry in aqueous solution. So if something is happening in aqueous solution, what does that mean the solvent is? Something is aqueous. AQ, we talked about that as a state symbol, right? Aqueous means dissolved in water, right? So water is your solvent. Water is a solvent for most things. It's a universal solvent. So let's take a closer look at H2O and see what happens, the very unusual, or let's say special case of H2O. So in a sample of pure water, you have nothing else in there except a bunch of H2O molecules floating around. What can happen if you have a couple water molecules is one of them can act like an acid, meaning it can give up an H+. And if it gives up an H+, where does it go? Well, you only have water in there, so it has to go to another water molecule, right? So the other water molecule here is going to act like a base, and it's going to accept that H+. So we end up with OH minus the conjugate base of this water molecule, and then if we stick an H+ onto this one, we end up with H3O+, the hydronium ion, which would be the conjugate acid of that. This happens in water all the time. Every time you have an aqueous solution, this is occurring. Do you have, based on this arrow, do you have a lot of these things? Do you have a lot of these ions? No. No. So we have very small concentrations of the H3O+ and the OH minus. Extremely small. Really, 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 really small. But they are there. And that is the key thing. And in pure H2O, what we see is that the concentration of the H3O+, right, remember the square brackets in concentration of something? We talked about that the last time? Yeah. Yes. I don't. The concentration of the H3O+ is exactly equal to the concentration of the OH minus in pure water. These are very, very small concentrations, really tiny concentrations. So for example, in pure water, that concentration is 1.0 times 10 to the negative 7 molar. That's the concentration of the H3O+. It's also the concentration of the OH minus. They are exactly equal in pure H2O. And when you multiply those two together, so the H3O+ concentration times the OH minus concentration, what do you get? Stick that in your calculator. Please, stick it in your calculator. So the concentration of the H3O+ is 1.0 times 10 to the negative 7. And you're going to multiply that by 1.0 times 10 to the negative 7. They're exactly the same in pure H2O. 1 times 10 to the negative 14. That is a very important relationship for H2O, but it's the basis for what we use in acid-base chemistry as well. That relationship is called the K, big K, subscript W for water. the subscript W here just means water. K just means that it is a constant, meaning that it does not change. So whenever you have an aqueous solution, when you multiply the H3O plus by the OH minus, you're always going to get 1 times 10 to the negative 14. It's the same value all the time. In pure H2O, these values are the same. But when do you ever have pure H2O? Never, right? But still, when you multiply those two, you're always going to get the same value, the KW, 1.0 times 10 to the negative 14. So let's take that idea now and let's run with it a little bit, or maybe walk quickly with it. And we can now come up with some relationships between the hydroxide and the hydronium. So pure water, pure H2O, is by definition neutral. And in a neutral solution, the concentration of H3O plus is equal to the concentration of the hydroxide. That defines a neutral solution. When those concentrations vary from each other, then we have other types of solutions. So for instance, if the H3O plus is greater than, right? So that's the symbol for greater than something. OH minus. So we have more hydronium than hydroxide. Then we say that that is an acidic solution. And then if the H3O plus concentration is less than the OH minus, what do you think we call that one? That's a basic solution. Or sometimes you'll see the term alkaline. So we can compare the concentrations of H3O plus to OH minus in a solution, and we can say whether it is neutral, whether it is acidic, or whether it is basic, by simply comparing those. A couple things to note when those concentrations vary or change. All right, so let's start in the middle here. We have equal amount of the H3O plus and OH minus, 1 times 10 to the negative 7. When the H3O plus increases, right, so it goes from here to there, what happens to the OH minus? It actually decreases, right? And it has to, because when you multiply these two, you should end up with the same KW, 1 times 10 to the negative 14. Right, so this is an acidic solution, more H3O plus and OH minus. The opposite is true as well. If you were to increase the hydroxide, the hydronium decreases. More OH minus than H3O plus, that makes it a basic or an alkaline solution. Let's do a little calculation here. So let's say that we have a sample of we'll do a let's say Pepsi has a hydronium ion concentration of 2.5 times 10 to the negative 4 molar. What is the concentration of the OH minus? So what are we going to use to solve that? What relates H3O plus to OH minus? So our KW, right up here, that's the only relationship that we know of that relates H3O plus to OH minus. So we're going to use that KW to do a little bit of math. All right, so we're going to use our OH minus times the H3O plus equals 1.0 times 10 to the negative 14. I need to calculate the OH minus. Can you rearrange that equation and have OH minus on one side? Yeah, this is just like what you did in the gas laws where you were just moving stuff around, right? But systematically. Same thing here. The only thing that may look a little challenging was instead of your P and your V, you now have this thing in square brackets. Right, we just need to isolate the OH minus on one side. So in order to have that, we're going to divide this side by H3O plus, which means we have to divide that side by H3O plus as well. Right, just like we did with our gas laws. So we'll divide here by H3O plus to get rid of it, which means you have to divide the right side by H3O plus as well. So that goes away. So our OH minus then, concentration is 1.0 times 10 to the negative 14 divided by the H3O plus, which was provided to us, 2.5 times 10 to the negative 4. Okay, and then you have to stick that in your calculator, right? Which may sound easy, but based on this morning's class, may not be so easy. So why don't you practice that right now? Evaluate or compute that using your calculator. Anybody? Taylor.
4.0 times 10 to the negative 11.
Times 10 to the negative 11. Yep. In the back?
Yeah.
Yes?
What?
4.0 times 10 to the negative. If you're not getting that, that means you're not entering it into your calculator properly. See me quick after class. All right, so you have to know how to put this stuff into your calculator. All right, that you're going to have to do this. It's a guarantee. You have to be able to do this. So we've just calculated what the OH minus concentration is in this solution. All right, so we have OH minus is 4.0 times 10 to the negative 11. Is this solution acidic, basic, or neutral? Is the is the H3O plus and the OH minus the same? Well, we're given the H3O plus, we just calculated the OH minus. Are they the same? No, so it's not neutral, right? Which is bigger, H3O plus or the OH minus? Which is bigger, the H3O plus or the OH minus? 2.5 times 10 to the negative 4 is greater than 4.0 times 10 to the negative 11. It's way bigger. It's 10 million times bigger. Okay, don't forget how you use and how you interpret those exponents, right? When you have a negative exponent, the bigger negative exponent means the smaller the number, the tinier the number. And the smaller the negative exponent means the bigger the number. All right, so because our H3O plus is greater than the OH minus, right, that would make this solution acidic. All right, and it should be because I told you at the beginning this was a sample of Pepsi, which is a carbonated beverage. They're always acidic. So we can use Kw to calculate either the H3O plus or the OH minus, and then we can compare those values to see whether your solution is neutral if they're equal, acidic if the H3O plus is greater than the OH minus, or basic if the OH minus is greater than the H3O plus. Okay, so you need to be proficient at manipulating that equation, right? You have to be able to algebraically solve for one of the unknowns, right? This is no different than the gas laws in terms of the algebra involved. What makes it challenging are the numbers, right? The numbers are all scientific notation stuff, and you want to make sure that you pay close attention to how you enter those in your calculator. All right, so we can determine whether a solution is acidic, basic, or neutral by comparing hydroxide to hydronium ion concentration, or we can do it way quicker by calculating something known as the pH of a solution. So the pH scale, or the pH of a solution, can be calculated and the pH is actually defined as when you write pH, by the way, it's small p, big H. It's defined as the negative logarithm of the concentration of H3O plus. That's how we define pH. In your textbook and also in the lab, you'll also see pH is the negative log of the H plus concentration, right? It means the exact same thing. H plus is the same as H3O plus, right? H plus itself is way too reactive to be on its own. It actually grabs a hold of water and it makes the hydronium ion. All right, so don't be confused when you see that. H plus is the same as H3. So you'll see them used interchangeably throughout your textbook. And if you Google stuff online, you'll see it used interchangeably as well. All right, so that's how we define pH. That small p actually always means negative log of something. And the pH scale goes from 0 to 14. And we're going to see where different solutions lie on this here in a second. We can calculate the pH, which we'll take a look at here in a second. We can measure the pH using a couple different techniques. We can simply use a pH meter, which is just a probe like this thing. And we stick it in a solution. And if you look closely here, it says the pH is 4.0. So it actually gives you a readout. There's not a whole lot of thinking involved. You just read it. But you have to be able to interpret it. The other ways that we can judge the pH of a solution is by using what are known as indicators, which you had some experience with in lab on Monday. And today you're going to be using the indicators in lab to judge the pH of different solutions. All right, so I mentioned the pH scale goes from 0 to 14. In the very middle, or the very center of our pH scale, with a pH of exactly 7, we consider that as neutral. Right? So pH of exactly 7.00 is neutral. Any pH less than that, so a pH less than 7 is considered acidic. And the further away you get from 7, the more acidic that thing is. So for instance, something like coffee has a pH of 5, that's slightly acidic, versus something like, hard to see, your gastric juice, is that what I see on here? Yeah, your gastric juice, which has a pH of 1.6. Very, very acidic compared to a pH of 5, coffee. Where would you find gastric juice? Out on the juice shelf in your supermarket store? Hopefully not. That's your stomach acid, right? And it's very, very, very acidic in there to help break down all the stuff that you eat and drink. And then on the other end of the pH scale, we have pHs greater than 7, right? And we refer to these as basic solutions or alkaline. So the further you get from 7, the more basic something is. So for instance, a lot of people think blood is neutral. It's not. It shouldn't be. If it were neutral, you would die. Blood actually is slightly basic. It has a pH of about 7.4, right? It's greater than 7, so that makes it slightly basic. Compared to something like, we have down here, that's a 1 molar NaOH solution. That's what you have in stuff like your Drano at home. Right? It's a very strong, very hazardous solution. It's extremely basic. So that's how we interpret that pH scale, right? pH of 7 is neutral. Anything above 7, pH higher than 7 is basic. pH lower than 7 is acidic. All right, so let's take a look at how we calculate the pH of a solution. Let's jump down here a little bit to this thing. So this is aspirin, which, by the way, is an acid. It's acetyl salicylic acid. And I believe we might be making aspirin in the lab at some point this semester. We make it, we don't use it in the lab because it needs to be purified and everything else. And we're told that a solution of aspirin has an H3O plus concentration of 1.7 times 10 to the negative 3. What's the pH of this solution? All right, so here, just a simple case of using that pH relationship. So the pH is just a negative log of the H3O plus. So we just substitute that into our equation, negative log, we insert 1.7 times 10 to the negative 3 molar. And you have to now put that in your calculator. And you type it in just as you see it. So do that. Tell me what you get. So negative log, and you enter it, close the parentheses, and then go, or enter, whatever it says. 2.76. 2.8. Okay, so there are sig fig rules for logs, which are very complicated. So I'm just going to say to 2 decimal places. What's the answer? 2.78? We'll go with 2.78. All right, so does that pH make sense? 2.77, sorry.
My log, every time I hit it, it says error.
Okay, so that's a user error. So see me after class, I can quickly how you enter it, in other words. So how you put it in is extremely important. And if if the syntax isn't correct, then it's not going to give you the right answer. Does that pH make sense? Right, aspirin is an acid. The pH should be less than 7. And actually, it may be surprising how acidic it actually is. All right, so if we're given the H3O plus, we can calculate the pH. What about if we're given the OH minus? Can you still find or calculate the pH?
I can't.
How? Right, so you can solve for the H3O plus first using the KW and then stick it into your pH equation. What about if you are given the pH and you want to calculate the H3O plus? So I think there's one, yeah, there's one down here. So it says determine the H3O plus for the solutions having each of the following. Let's do B. So this is telling you the pH of this solution is 3.42. And we need to calculate the H3O plus concentration. So there's a relationship that manipulates the log function to help you solve that, right? And it goes as follows. The H3O plus is simply equal to, I'll write that bigger, is equal to 10 raised to whatever the negative pH value is. Right? So if I'm given my pH, then the H3O plus is simply 10 raised to the negative, and the pH was given as 3.42. Right? And again, you have to enter that in your calculator. You have to evaluate it to get an actual number. Don't leave it as 10 to the negative 3.42. So what do you get? How do you put it in? There's several ways you can do it, right? So there should be a button there in your thing that says 10 to the x, for instance, as a second function. Okay, and you have to enter x as a negative 3.42.
We put it in the scientific.
So I would like the answer in scientific notation, yes.
So it'd be 3.80 times 10.
10 to the negative 3.42. You guys are going to make me do it myself? Okay.
3.80 times 10 to the negative 4.
You're just typing in 10 raised to the power of negative 3.42. Yeah. 3.8 times 10 to the negative 4.
Yeah.
Yeah, 3.8 times 10 to the negative 4 molar. Okay, if you're not getting that, or if you're having trouble entering it into your calculator, that is a problem that you want to get fixed ASAP.
I'm sorry, where did we get the 3.8?
After you enter it in your calculator. Okay, you have to be familiar with how your calculator works before the exam. Okay, you shouldn't be fumbling around when exam day rolls around trying to figure out how to enter numbers in.
So like, what's the equation?
The equation is 10 to the negative pH, gives you the H3O plus. That's what the equation comes from. You're trying to solve for H3O plus, so we just type it into your calculator.
But that's how you'll, once you put it in scientific notation, do that. Okay, cool, thank you.
Okay, so we can, if given the H3O plus, we can calculate the pH. We can also go in the other direction. If we're given the pH, we can calculate the H3O plus in a solution. Let's summarize some of the relationships that we've seen thus far. As the pH decreases, what happens to the solution? Does it become more acidic or does it become more basic?
Acidic.
As the pH decreases, what happens to the concentration of the H3O plus, the hydronium? The H3O plus goes up. There's more hydronium ion that makes it acidic. What then happens to the concentration of the hydroxide? It decreases. Right? So I'm trying to set it up in a relationship that makes a little sense to you based on what we saw with our gas laws, right? Is there a direct relationship? Is there an inverse relationship? As the pH decreases, there's a direct relationship with the hydroxide, right? The pH also goes down. I'm sorry, the OH minus goes down. There's an inverse relationship with the H3O plus. The hydronium goes up. As the pH increases, the solution then would become more basic or alkaline. What happens to the H3O plus? Your H3O plus concentration will go down. And your OH minus, the hydroxide, is going to go up. So there are several things that happen when the pH of the solution changes, right? In terms of the acidity versus the basicity of a solution, but also in terms of the relative amounts of the hydronium and the hydroxide, right? In a basic solution, you have more hydroxide than hydronium. In an acidic solution, you have the opposite happening. The pH value quickly tells you whether something is acidic or whether it is basic based on the pH scale.